Wow. That's good. So this is called a relaxation spectrum. So what is that? So let me just, so I added that to, where's my power? Oh, I got to go here. Hold on a second. Where are the slides here? First thing, I added something to that one. Did it download it?
Yes, it's down. That's it, now.
Where?
On the yeah, now that
Oh, it's below.
Yeah.
All right. It's pretty frustrating when you can't find something. You know, it's like, is it because I'm going senile, or is it like, you know, you wonder. All right, so this is the thing. Like if you have, like we had this, the compliance, and there's the instant compliance, the unrelaxed compliance, and the relaxed compliance. And the two values, the unrelaxed is a high, that's like a solid, and the relaxed is a liquid. So the ratio of the unrelaxed to the relaxed, this is a huge number, like 1,000, or maybe 10,000. Like in other words, what's the modulus of a liquid compared to a solid? It's a big difference, right? So anyway, so that's the unrelaxed one, the solid one, and you're gonna have some of these relaxations that are kind of exponential in form, right? This kind of exponential decay things. In fact, for the compliance, it's 1 minus exponential, right? Because it's 0, it's full, and then it decays. So this thing decays with time. Anyway, so anyway, if you have more than one relaxation, you're gonna have a sum of these adding in. So you have like each component. So this is an amplitude and then a time. Like each one has an amplitude, a magnitude, and a time. Right. So you can have a plot of magnitude versus relaxation time, and that should have kind of peaks in it. Say there was just one, it would be a spike, it would be a delta function. Right. So that spectrum would be this like LJ for the compliance. And that's based on this tau. And then when you convert to modulus from this, you get the same equation, but you have this H, which is the relaxation spectrum for modulus, and then this tau hat. Tau hat is like 10,000 times bigger than tau of the compliance. This is all in the Strobel book, kind of in that part, right? So it's kind of condensed from that, I guess, but these are actually his equations. So anyway, so you have this compliance. So then basically you can talk about a spectrum, the material having a spectrum, like the response is a spectrum. Right. So in other words, you can do it for the dynamic, or you can do it for the time, for the frequency one, or for the time one. Right. This would be the spectrum times exponential for each component at that tau. And this accounts for that kind of that exponential converted to frequency space. Right. So anyway, so that's the deal. So you got to talk about relaxation spectrum, and then like in this paper, so he has this plot. So he has that times tau. So why is that? Why not just plot the relaxation spectrum? So it's because this thing's set up in a log scale because this thing's an exponential. So you want to have a log of time of that thing. When you do log d log tau, that's the same as dt over tau, and then tau times hg becomes the thing you want to plot versus tau. So first off, the first thing in the paper is kind of confusing, like, what is this? Now you can see it's got humps in it. So each hump, so if it was just one relaxation time, it'd be a spike, and there's some dispersion in it, and it's got this kind of hump character to it, right? That's number one. The first thing you see, like, you don't know what he's talking about. So it's a spectrum. Then he's talking about something called Janus. This is a paper about Janus nanoparticles, right? So that's a whole kind of field to itself that you probably should know a little bit about, but not too much, because it's probably worthless. Most likely like worthless. Let me just hide this thing. But basically you'll hear it, so you might as well know what it is. There's a lot of aspects of this Janus thing. So let's see, I put these at the end. So there's a review on Janus nanocomposites. That's one area of it. You don't need to read this, but you could look at the pictures if you want. From Hunan, China, or Wuhan, China, Hunan province. Coronavirus. Yeah. the death city. You know, you look at I mean, and then you start looking at the Google Maps of China, right? And it's like, oh my God, there's a place, Wuhan, it's got like 20 million people living in it. It's bigger than New York City. And like, you never heard of it. And not only that, but there's like 15 or 20 of these cities that you never heard of that have 20 million people in them. And they're all connected together. Basically, we know nothing about the world is what it comes down to. We're living in this little isolated thing, you know, so it's good to have a broader perspective, I guess. But so Janus was a Roman, says no Greek equivalent god. There's a Roman god, and it's the January is named after Janus. So it's like the doorway god. And it's also the god, all right, so the Romans, they had a gate, they had a temple, not a temple, but it was just a wall with a door in it. All right. And then when they went to war, the door was open. When they had peace, the door was closed. So it's seen as like good and evil kind of also, you know, and also beginning and end. So Janus is kind of like a thing that's useful and to talk about, like you could pray to it or the Romans did, you know. So anyway, it's a two-faced thing. One's kind of happy face, one's sad face, more or less, you know, beginning and end type. And January is named after it. So anyway, the idea is like, you got to make nanoparticles that have two faces to them. They have two sides. So the one that's kind of seems to be most popular is you do all right, so flocking is another topic. So this kind of leads down a rabbit hole, but like flocking Janus particles, this is the whole area, right? So this guy Steve Gannick is kind of like a famous polymer guy, I guess. Now he's in Korea, like he cashed in or something. But anyway, so the idea is like you make it this with, so you can make this make particles at an interface, and you kind of coat one side with something that can react with hydrogen peroxide, and hydrogen peroxide like foams, you know, so it'll give off gases and it propels the particle. So you put it in water with peroxide or alcohol, then these things will fly around like birds. And if you can tune that flying, you can make them flock and you make them swim and do different things. So basically that's kind of the idea. So you can do that with hydrogen peroxide. That was the main way. And then there's other ways people talk about pH and magnetic fields and stuff. So it's basically you have particles that have two sides, then you can make them do things like make structures, some kind of coordinated motion. It's called emergence, like an emergent structure, like nature has emergence. You can see a flock of starlings and it forms different shapes in the sky. So you can do this in a computer simulation pretty easily. Like you can make particles like that and then make them flock and things in computer simulation. And you can also kind of do it in experiments, you know. So no use, absolutely no use, right? But people are interested in it. That's like one aspect of Janus particles. Another aspect is the nanocomposite end of it. So there's a lot of kind of useful topics in this paper. So that the nanoparticle part, this is a review of just the nanoparticle thing. So like in other words, not nanoparticle, but for nanocomposites. Right. So the idea is that, oh, that's this thing. All right. So the other review, that's the flocking. This is the composites, right? So anyway, so in this case, there's something called a Pickering emulsion. Okay, so if you take like oil and water and you throw flour in and you stir it up, and you can get the flour will like surround the oil droplets and stabilize it, so you get smaller droplets. So it's used in food science a lot. So I don't know if Pickering was a British guy, but in the 1800s or something. So it's been around a long time. Anyway, so then Janus particles, and they said like, oh wow, you know, you can make a Janus particle that would like the oil, and the other side would like the water, and then you can make like a magic Pickering emulsion where you kind of control it a little bit more than flour and water. So people looked at this like stabilizing colloids with these Janus particles, and then that becomes like something like using a block copolymer is another way to stabilize a mixture of two polymers, say. So you have a block copolymer with polystyrene and PMMA, and then you put it into a mixture of polystyrene and PMMA. They don't mix, so the styrene part goes to styrene, and they go to the interface and lower the interfacial energy. And when the interfacial energy lowers, you can get smaller domains of PMMA or polystyrene, or whatever you want to put into anything, right? So that's pretty well known to use block copolymers. And there's a bunch of things I'll talk about next week about like how the molecular weight, you change the molecular weights in the two components, and you can control the phase size and things, right? So anyway, so that's kind of that's where the nanoparticle Janus nanoparticle thing comes from, and people have been doing it for a little while. I mean, this isn't something necessarily that new. In fact, they show in this review paper the thing that this guy's doing. So what he's doing is he's taking so he does what's called latex polymerization. So you take water, right, and you take PMMA, which is like oil. So PMMA is here, I can just get it here somewhere. Wiki PMMA. They should show what it is. So it's basically, this would be, if this was OH, that would be like a carboxylic acid. And then there's a methyl group here. So it's methyl acrylate. That's acrylic acid. So it's called methyl acrylate. And then there's a methyl here. So it's polymethyl. That's that one. Methacrylate, that one, because an acrylate with a methyl on it. So that's plexiglass. That's like kind of popular polymer. Anyway, so there's that guy, and then there's polystyrene. I think you guys know what polystyrene is, right? Go to the source of everything. The styrene is just an aromatic on the side. So this doesn't have an oxygen. That does have an oxygen. That means you can, if you do a TEM and you can do elemental analysis, you can find the oxygen one lights up, the PMMA, and the other one doesn't light up. So you can do both in one. So he does that. He does that in here to show that this is working somewhere. There's the one color graphic in here somewhere. Someplace, somewhere over the rainbow. Here. So see, he's got the two Janus particles. It's like a two, so one's styrene, one's PMMA, the one on the left, and the other one's styrene. Then he does oxygen mapping. He gets just the PMMA part, the oxygen shows up. So he says like that thing. He zooms in on that, does the EDEX on it, gets that. So that kind of works out. This is carbon, this oxygen. All right, so he's demonstrated pretty committed. All right, yeah. Let's see. All right. Red is carbon, green's oxygen. And it's all the same particles, that particle. Yeah, you can't see it all. See it pretty good here. I can see it perfectly fine. So anyway, you can kind of see it. Let's see.
Oxygen is kind of.
All right, so it's that exact particle, just zoomed in on it, and he does carbon on the left and oxygen on the right. He knows it's TM, it's TM. Yeah, so he knows pretty much like what that is. That's pretty good. There's a lot of good little analytic things in here. Problem is, he kind of goes off the deep end, like it's too much, right? So he makes the things by, so you do latex polymerization so that oil and water don't mix, so that PMMA, the methyl methacrylate monomer, wants the phase separate. So you put a surfactant in. So you use benzyl. So the most popular surfactant is this SDS. This dodecyl. So it's also called SLS, sodium lauryl sulfate. They're the same thing. So basically 12 carbons, and you put a sulfonate group on. So this comes from cows. Basically, this will have three, so it's a triglyceride fat, that's cow lard. They do this in Cincinnati and Ivorydale. Then you cook that, you break apart, you get glycerol from the top part. So it's a alcohol with 3 OHs on it. So it's like propane with 3 OHs. And then you get these fatty acids off it with an OH. Then you stick it in sulfuric acid, you get this. That's detergent. So you go from a dead cow to a detergent. So the clean stuff and the dirty stuff like come from the same place, right? And then if you put an aromatic in here, that's this sodium lauryl benzyl sulfate, right? So they try to put different groups in here to modify how So SDS also has like people have skin rashes from it. So they try to modify it to make it nicer for your skin or something. So they put in different groups and basically you just can stick different groups on the end of this. You can have another ether group in here as the common one for commercial soap and things. Anyway, so yeah, that's what they do. So they just put that surfactant in and then they polymerize within those domains. And then they also put this guy in, divinyl benzene. This is like a common like cookbook thing. So you're gonna stick this in, it's got two vinyls, both of those can polymerize. I mean, you can make a chain here, you can make a chain there. You put enough of that in, you just make a network. Like this is a substitute for the methyl methacrylate has a double bond in it, a vinyl that opens up and makes a chain. And the styrene also has a double bond in it that opens up to make a chain. In fact, if you get rid of one of these vinyls, that's styrene, right? So stick this in. So it's a natural cross-linking agent for styrene. So it'll just make you have like a 4 tetrafunctional cross-link, like the chains go here and here. Anyway, so you stuff some of that in, and then you can this will make a solid particle. And then you control the size by the amount of surfactant that you put in. So you can have a nano-sized sphere, perfect spheres of PMMA. So that's latex paint. That's how you make latex paint, water-based paint, like the oil-based paint, and then water-based paint. Well, all the water-based paint is this, right? That'll be white when you come out, depending on how big you make the droplets of it. So you make white paint, and then you take that, you purify it, and then those things will serve as seeds for polymerization of the styrene. And you put in divinyl benzene, and somehow he cooks it, and you can get that thing. I don't know how that part works. This part up to that point is white paint. That's pretty easy. After that, but this isn't uncommon, because if you look into that review paper, they go through this exact process. Like they tell you exactly how to do that. Just gonna dump that in with a mixture. He's got a micro extruder that holds like I think it holds like 10 ml. So it's like an industrial extruder that holds like a truckload of polymer, and then you make it really small. And then you can do an extrusion with it and mix things, you know. So you use a micro extruder. He doesn't have much of the stuff that he made. And then he mixes it, and he gets a nanocomposite from that. He gets the domains of styrene, and then the PMMA, and then he has the interfaces covered with these particles, right? And stabilizes it and can control. So how does the rheology of that thing look? That's kind of his question. Then, all right, the curvature of these. All right, so this says a lot of little things on this, okay? The other is this Marangoni effect. This is another topic that is absolutely worthless. Like Janus particles, like you should equate that in your mind. You hear the word worthless, you know, so your response should be Marangoni stress, Marangoni effect, worthless. Like those things should be in your mind, because even though people, all right, if you make it right in a proposal, it can sound pretty good, but basically it's not. All right, so Marangoni effect, okay. So I can show you how bad things get, but let's see. Let me just get rid of this thing and start. Why did that show up? I just want a new one. Go here. Right, so we can blame the Marangoni effect, 1997. Okay, so Marangoni effect was around for a while. When you have all right, you can wiki that too. Marangoni effect. The coffee ring part, this shows it pretty good. So basically you got particles suspended in the wine. The wine goes up at the edge of the glass. So this all has to do with food, and like food that isn't good for you, like coffee and wine and stuff. So basically that's why it's so popular, you know. So anyway, it goes up, it evaporates, the particles get more concentrated, that drives more flow up into the top. So that's the Marangoni effect, is like the evaporation, and then you get a concentration gradient, and it wants to dilute the concentrated one, so it drives up, so you get this effect that's best shown on the wiki page, I think, but you need to shoot a light through it and get a shadow. Remember one of the papers they showed the shadow images? wasn't that one of the papers we looked at? They did shadow imaging. So this is a shadow image. So you can't see it when you look at the wine glass, but if you do a shadow image, you can see the Maragoni effect, like it forms this ring up there. Okay, so that was this is exactly the thing. Yeah. So the coffee ring is where people started making money off this. Okay, like because right, that's good. All right, so the coffee ring. So all right, so all the it's kind of disappointing because they're like the major figures in polymer science. Like Tom Whitten is a genius. You know, he was at University of Chicago. This was when he was an assistant professor. He didn't make tenure. So then he went to Michigan. In between, he went to ExxonMobil in Annandale. And he worked with, and he was the smartest guy there by far. You know? So he became like the brains behind all like the packing factor. And then also the packing factor, he originated that with the copolymer thing. And then he was at Exxon and they turned that into a whole industry, him and Lou Fetters and the other guy. So basically, Whitten is really bright guy. So anyway, but here he's published this 1997 on like coffee stains, like what happens and the Maragoni effect and the coffee stains and how the beads work through. This is probably his most cited paper. It's like you have Einstein and his most cited thing is this Einstein viscosity equation. He says, I wish I had never done it. You know? And then this is kind of the Tom Whitten thing. So anyway, so that's a you can glance at that if you want. And then even more embarrassing, this guy, so Whitten is like a simulation guy. Then Ron Larson's an experiment guy, like a rheologist. He won the Bingham Medal in the Society of Rheology, like the top medal. Anyway, so he's like a kind of a blue collar. Whitten's like kind of like a floating genius, and Larson is kind of like a really blue collar, hard work gets results type person, you know. So anyway, coffee rings, yeah, same thing, you know, and how the Maragoni effect. This paper has like 2,000 citations because it's coffee rings. So you got your wine glass and your coffee rings, and then like Larson's written books, you know, that have like a couple hundred citations. Like the most important papers of his, maybe they have 30 citations. You know what I mean? So then this thing on coffee rings. So and what value is this Maragoni effect? Well, all right, it's debatable, but basically they've tried to find uses of it because it had so many citations. So they say, like, if you're going to spin coat and you want to disperse like particles on a silicon wafer to do whatever you're going to do, then this Maragoni effect can counter the fact, this kind of drying effect that drives the particles out. So you can get a concentration gradient. You can set it up so the concentration drives it to be dispersed better. So they talk about Maragoni effect being used in semiconductor processing. But that's really stretching it, you know, it's basically like a waste of time, you know, so.
There was some application relating with the polymer rebound stuff, so that they use this coupling effect to manufacture, synthesize the polymer rebounds.
To do what? I don't understand.
The polymer rebounds that can be like implemented in soft robotics or some stuff.
Mm-hmm.
So they need to use this coupling effect to produce those polymer rebounds.
I see. Yeah, okay. All right, that's good.
Yeah, that's good.
Yeah, that's good. That's pretty good. I mean, it's like they spent billions of dollars to develop aerogels, and the only use they ever had for it, well, they used it, the original argument for $1 billion was to make a fusion target, because it has no mass, and you can hold whatever in it. I think they didn't really do that because they go into magnetic something. So then the other thing is to collect space dust on the space shuttle wings or something, you know, because it's got so many surfaces, it stops the particles. So $1 billion isn't really worth like a space dust collector, a vacuum cleaner or something, you know. I mean, but so it's similar, like you get these things, you want to be careful about, it depends what you want to do. If you want to get 1,000 citation paper, it's probably good to jump on the thing. But if you're trying to actually do something, or if you want a job, you know, maybe like this isn't going to help much in a job. They're going to say like, we don't care about coffee rings much, you know. So anyway, so he's making this argument, and this is common, and this isn't unique to him. I mean, another use for the Maragoni effect, you know. So you have the Janus particles at the surface, and then when the particles come together, you get a depletion, which means there's a concentration gradient, and it wants to it wants to flow in to separate the particles. So they call it like a Maragoni stress-induced separation of the particles. Right. So he's got a lot of nice little stories in here, and he's used a lot of catchphrases that could draw some citations. Like if you cite papers that have 2,000 citations, when people go to that paper, then they look for papers that cited it, then they find your paper, and then they cite your paper too. So it's kind of like a hanging out with the right people gets you somewhere, type thing. So anyway, so that's a common theme of like how you do citations, I guess now. Anyway, so he's getting these two relaxations. So first there's a relaxation that's just due to the polymers together, right? So you can show that, he shows that down here somewhere. So he shows the pure polymer, I think it's S9, S8, S9. This is a pure polymer, it's just got the one hump, right? The black is PMMA, the red is polystyrene. So they have their relaxation spectrum. They have a relaxation time, like a glass transition. That's it, right? So that hump. Then when you mix them together, you get this other hump shows up, and that's the shape hump. That has to do with the shape. That's his tau F here. So he's got this tau F is like the shape of the particles, and he can shows in here that the particles get, or the polymer domains get larger and smaller. That tau F moves around. I don't remember if it goes left or right. And the tau beta has to do with this Maragoni thing. So you can make that disappear by, instead of making droplets, he does a spin coating thing. So he spin coats and makes layers. He puts his particles at the interface of the layers, and then he takes that and puts it into a cone plate rheometer. All right, so also, and then another thing he does. All right, so there's a lot of little pieces to this that are interesting. The whole is kind of worthless. Okay, this is kind of a funny paper because it's got a lot of pieces that I think you should probably know about: Janus particles, Maragoni effect, this idea of like going spherical to plate to kind of get rid of those shape factors and things. So there's a lot of things that are pretty good. So he's picked up on a lot of good things and crammed them into this paper, right? So anyway, so there's that business. Then what else? Something else I was going to say. So he's, and then, all right, he does this other thing. So normally, if you wanted to get this wide spectrum, right, wide, so look at his range here he's got. So he goes down to 10 to the minus 2 seconds, right? And then he goes up to 10 to the 3. So he's got like, I don't know, 5, 10 orders in magnitude, right? So it's too much. In one measurement, you get one order. Like if you just do one temperature and you do oscillatory, you get 1 decade in frequency, maybe 1.5. So if you want to get more, usually like change the temperature. So you do time temperature superposition, you can move the things around. He doesn't do that. He goes to the relax stress. He measures the compliance. So he does a pulse and then he watches the thing relax, right? And then he converts that back to modulus. The H is the spectrum for modulus, L is for compliance. So, and because that's such a slow process, he can get can expand the frequency range in this thing by doing that. Okay, so we can get the low end with the compliance, and they can couple this together without using time temperature superposition. Because one thing, time temperature superposition is going to have a problem when you have solid particles in there, because they don't. So say you put 50% carbon black into rubber, right? Well, yeah, there's a time superposition for the rubber. Yes, absolutely. So you can get an AT for the rubber, but the carbon black has none. The carbon black is just a rock, right? So that means half your sample isn't going to time temperature superposition, but you're still shifting it with AT. So something bad is going to happen, right? So basically, if you do this compliance thing, you don't need to do that. So it's kind of a way to get around it. But so that's kind of interesting that he does that. Let's see. So to do that, though, anyway, to do that, he goes through a whole range of things here. The Schwartzel method is the way he does it. It's a way to convert compliance to modulus, and it involves basically, as far as I can see, this is like an empirical function that's going to kind of convert compliance to modulus. Modulus is omega in here, I think, in this paper. So this is from a while ago, 69. So this is all the groups he cites are German groups from the same school. So it's all like within the same club type thing. So anyway, so that's kind of interesting that he does that. And for nanocomposites, that kind of makes sense that he would do that. Then that's one thing he does. And then what else is going on in here? Maragoni effect. Something's one other thing. The idea of using the sandwich versus that, so he can remove that feature from it. It's pretty clean. Like he shows micrographs, he shows the particles at the interface. It's something like here, so it's kind of like decorated. And he also explains why, like you say, there's not enough particles there to really have any impact, but he explains exactly why that is. It's because, I mean, the way he explains, you have the inside particle and the outside particle, and when you have a curved surface, the inside particles are more crowded than the outside particles. Actually, a small concentration where you can actually fill the surface with particles because it's curved. The more curved it is, the lower the concentration because the inside ones jam. Then he talks about a jamming effect on the rheology, on the G prime, G double prime, and that shows up as a peak. So he's got, and it apparently, all right, so it sounds like he's just going off the deep end. All right, so he's got like the peak from the shape is this shift, and the peak from this interface is this other shift over here, which you can't see. So he does that transformation to get his spectrum, to get his relaxation spectrum, where you can clearly see there's multiple humps in it. Right, so that's using that, whatever this, not the Schwartzel, the other thing. But so anyway, so there's that business, and then there's this other thing, the Polymer analysis. So this is a really complicated thing. So that's what I mean. Like this paper's, but it seems to work. So he ends up with an equation that he shows in here someplace, equation 2 or something, I think, which describes all these parameters that you can get from just see if I can grab that. This equation, not that equation. Yeah, this equation. So this is the Polymer thing. Where's that? Oops. Hellier and whatever, Strasbourg's near Freiburg. So it's kind of like a similar area. So anyway, this he can convert and then parameterize his dynamic modulus he's getting out of this thing. Right, so he parameterizes it into this. So you can get numbers like the interfacial tension is gamma, and then the beta is a shear modulus. So you can get like real numbers out of this fit of the complex. And all right, it looks like you can't tell if it works or not, because I mean, the only way to tell if it really works or not is in, all right, you can see like how many times has it been cited. So it's been cited a lot. And then you can see in terms of the parameters he gets, like the surface tension changes with the concentration of the particles he puts in, and it drops, which it should. So that's good. That's well behaved, and then you can fit that with an exponential. Big surprise. So everything's exponential, right? So, and then he can fit the other thing to the shear modulus, and that has normal behavior. So it looks like he's hanging from a thread here. Like he's got this. Well, he's got a curve, and normally if you just measure this and say, oh, well, there's something going on, and then you just walk away. But here he's fit every little feature of this thing. And then he does transforms to bring the features out. So that kind of makes you wonder. So the other thing, I mean, so that's interesting, you know, that you can do that fitting to get those parameters, and it kind of seems to work. I mean, it seems convincing that it works. And then he also says, like, I see you can have different kinds of domains. You can have spherical domains, or if you get to a high concentration, they can merge together and get like a network, like a bicontinuous structure. So you can have like a spinodal structure. You have one phase continuously passing through like a web. So you have a web and then a thing, matrix of a web type thing, right? So when he gets to high concentration, he says he gets to that. And then at that point, you go to this winter network thing, which says that the storage modulus should be a power law and frequency. And the storage and loss module should have the same power law if it's a network. That's Henning Winter, UMass guy, right? So the guy that Ben Yevitt worked for. Right, so here's that power law shows up when he gets to the spinol, like well, not spinol, when he gets to like a co-continuous structure. None of these are stable, like they're all non-equilibrium. So basically, in the time when he's looking at it, it's a network, and it shows that kind of network behavior of G prime. It shows up there. So that's good. I mean, that's kind of interesting. So he's done a pretty thorough job of looking at this thing, like the power law dependence and frequency of those relaxation times. And there's a lot of things in here. So anyway, I think that's everything that I got out of this paper. It's kind of a long paper. It's kind of complicated, but he talks a lot about jamming, about how the particles jam, and that's another topic. That's another topic that people are like popular. Like if you can write a paper that has the word jamming in it, then you're probably going to get cited more. You know, because jamming in physics is like an interesting topic, I guess. And that actually has some importance, the jamming idea. Like you have piles of sand or something, why does it have that slope or some other slope? That kind of idea. You know, how do the particles stick together? And glasses, jamming is kind of the basis of glassy behavior, glass formation. And for his case, he's saying the particles are 2D jammed, like there's jamming going on with these Janus particles at the interface. I could have pulled up some papers on jamming too, but there's too many. Like these things, there's only a few, there's like that Nature paper, the 2000 citation Larson papers, there's like 10 papers on whatever that was, but it's the Margoni effect. But if you talk about jamming, there's like thousands of papers. It's like everyone and their brother is doing jamming of particles. This is when you're working with particles, they jam. And that's an important feature of it. So anyway, so he talks about jamming too. So that's a whole subject of itself that I didn't mention here. Anyway, so let's see what we got. So figure 7 shows storage and loss. The data is from both these two techniques, right? Creep measurement and small angle oscillatory shear. I can never remember that acronym. SAOS, right? So very low frequency using the Schwarzschild method, which is that, I'm going to have it up here, like the Schwarzschild thing. So this is too complicated to read probably, although you can recognize some things in it, like that equation. So that's exactly the equation from what I showed you. And F of T would be the relaxation spectrum, right? So they're just shelling out the same thing over and over again. This 1 over omega, that's the definition of J naught, right? Is this kind of viscosity times frequency gives you that. That means you have flow, right? So anyway, so this paper you could pick apart if you wanted to, but it's kind of, the typeface makes me think it's written in the 1800s, you know, isn't it? Like you look at it and it's like, I don't know what font that is, but it's like the 1800s science font, you know? So anyway, you can look at that if you want, but basically I'm just saying, like, explain how the broad range, so usually, how do you usually obtain it? So you use time temperature, so you should write the either WLF equation or something like an Arrhenius equation to get a shift factor, to shift omega. And then they shift the G is just randomly shift to make it work. And all these papers will say like, oh, we use the shift factor for G. They won't say like, what's the basis of that? Because there is no basis. They just do it to make it line up. So the time part is fine. The other part is a little bit weird. Like, why is that happening? It could be because it's put filler in it. That could be where the filler thing shows up. Anyway, so like if you write the Einstein equation, it's 1 plus the concentration of filler, and it's just going to be a shift factor up and down of the modulus. If you just take that equation without frequency dependence, that would explain the shift up and down in a filled system, but you could explain it hand wavingly. So then he says, explain how the broad range is usually obtained, time temperature. Then he shows the shoulders at low frequency. So the shoulder is the shape factor. And then why does it change with concentration? Because you put in more particles, the shape of the particles, the domains get smaller as you add more Janus particles. So that means that shape factor should shift. And he shows that happens with the concentration of Janus. That also verifies that they're at the interface. and if they're modifying the surface. And this subtle increment is this business of the Marconi effect, like something, and just whatever BS you want to say about it, like something's going on at the interface. And that thing disappears when you go flat. So it's got to have something to do with curvature and packing and whatever else he says in there. He piles it on. So basically, the last thing is like, you can elaborate on it if you want. He says a lot of things. So, and he seems to support whatever he says. Polymer model that describes the bulk and disperse phase dynamics. So that's the fitting function to get the shear at the interface and the interfacial tension from the modulus measurement, from the dynamic modulus measurement. Describe say what a Marconi stress, which you might have said here, and then other components. There's other parts like the Polymer model. He describes it pretty well, better than the Polymer paper. There's two Polymer papers up there. There's one, the Polymer paper itself, which has like 1,000 citations. So you can see like people are using this. It isn't. And then, I mean, normal citations you're going to get is like 10. You know, if you write a paper, any paper you write, it's going to go 10, 15, maybe in a while it'll be like 20. So 1,000's a lot. Once you get above 1,000, that's a seminal paper. You know, it's like a major thing that people are using. Then even the analysis paper of the Polymer has 387 citations, right? So this one's kind of complicated to read, and then the other ones should be simpler because it's application of it. I'm not sure that's necessarily true, but this one's like application by some other guys in Germany. Everyone's in Germany here. So that's why is it Marconi not? It's not present in layers because there's no curvature, so there's no squeezing of the particles. So you don't have two domains that are going to come together and push apart the particle. Everything's a layer, so it doesn't happen. Right. So then he shows Cole plot, which is useful to kind of see that people use that, I guess. So he's got this one. It's a single relaxation. So this is just a Debye relaxer, right? And then he's got the multiple when he puts in the particles. So it's it's almost like the same thing as a relaxation spectrum. It's a totally different plot. Looks exactly the same, right? It's got humps. Each hump has to do with one relaxation time. I guess the difference is if you had a single relaxation time Debye relaxer, the Cole plot would be a circle, whereas the spectrum would be a spike. So the spectrum has more information. It's telling you it's polydispersed. Like you have all these relaxation times around a central peak. Whereas the Cole plot, if it was polydispersed and monodispersed, it would still be a hump. It's the same thing almost. It shifts the peak around a little bit and up and down, but basically it looks the same, right? So that's a Cole plot. And then when he has the others, there's multiple peaks, and he has peaks for the F and the beta in this also. So you can get the same kind of thing from the Cole plot. It's just, and it looks like the same see, here's the other one. It looks almost exactly the same thing, right? But anyway, so that's worth kind of looking at. Explain what it is and what you can get from it. That's basically analyzing it in terms of a single Debye relaxation when you use a Cole plot. You're looking for circles, semicircles. Figure 9 show the weighted relaxation spectrum. It shows peaks. Looks what I just showed. It looks like the other one. Interfacial, compare with neat polymers. S9, I talked about that. The S9 doesn't have the other peaks. It only has one peak. Like the one with the pure polymers just has one peak, just a glass transition. And then storage and loss moduli. So basically that's that's from the lecture notes, like from this thing. So how do they relate to storage and loss? Well, this is the complex modulus. So basically you integrate it. This is going to govern how you get the storage and loss. This should be G star here. So it's going to be the integral of the spectrum times times a Debye relaxer for each tau of the spectrum. So still this is a single Debye relaxer, like 1 exponential minus t over tau converted to frequency is going to be that equation. And then each one is weighted. The amplitude of it is that spectrum. So then you get the complex modulus and you can get the storage and loss from that. That's the idea of this thing. So, and then moduli, figure 9 that show the dynamics of co-continuous. That's where you see this winter thing. This, in other words, G prime scales with frequency to a power. So that signature of a network, and he's saying it's the materials in networks. That's consistent. Plain origin of equation 12 and 13 is done in class, how they used to show that figure 12 different than figure 9, later multi-layer structure to show different dynamic behavior to bulk. So that's kind of the same thing rehashed, I think. That's 12 and 13. 12, that's just the same. That's the spectrum, right? You're gonna have modes, each tau I and GI, so it's a sum of different. That's the same as this equation, except it doesn't have the GU. It's kind of the same as that. Or it's this summation equation for G. Oops, what that is. Mm. I added this. So that's the idea that you can make separate Debye and atom together. It's called the Boltzmann superposition principle. So you'll see people talk about Boltzmann superposition. That's just that summation. So usually, theoretically, you can't talk about a single relaxation time, and you talk about Boltzmann superposition for the real things. I don't know. I talked about this is what we did last time. That's a winter thing. That's just Rouse behavior. So I don't know. Anyway, it ties into this, but I don't know. It's basically I added this thing. So the spectrum thing, and then just a picture of that. But anyway, so it's pretty involved. But hopefully you can do this. I don't know. It's a lot of different things in it. So it exposes you to a bunch of different things. Next week, I want to do nanocomposites. So kind of as a lead into that in science, because it's got nanoparticles put in for a particular reason. So hopefully it's okay. Yeah, so I don't know. Any other questions or so I might quit there. Yeah. All right. Yeah, have a good weekend.